is my co-author, Tomasz Komorowski, which is now in Poland, very close to the border, and Joel Lebowitz, that most of you know, maybe the young one don't, but the big master, and he's very active, and I saw him last week in great shape, and he has inspired this, this work. I mean, this is about understanding how work becomes heat from the microscopic level, and this is one of the main problems in thermodynamics. So we try to understand this on the most simple possible model. And, and the model is this: we have an harmonic chain, one-dimensional harmonic chain, composed by n atoms. Each atoms, let's say, are mass 1, and there is this harmonic spring between two atoms, plus there is a pinning. Each atom has another harmonic chain to pins it. So I will denote by each position of the atom is denoted by qx. X is the position in the lattice, and it has a velocity px. Okay. Okay, this about the interaction between the spring. There is a potential u qx minus qx minus 1, which is just harmonic. I will say something about the non-harmonic case, but which is much more difficult. So it's just a quadratic interaction. There's a potential of this spring between qx and this x and this x minus 1. And there is another pinning potential, which are the form omega 0 square qx square over 2. So when omega 0 square is strictly positive, we have a pinned chain, otherwise than pinned. And it's very important if there's pin or unpinned, because we see the unpinned chain will have another conservation law beside the energy. Then the harmonic dynamics will be perturbed by some stochastic mechanism to make it diffusive, to make the energy diffusive. And the stochastic mechanism is that there are at exponential times, independently, each particle change the sign of the velocity. Like if there is a collision, elastic collision, with an exterior particle of a reservoir of infinite mass. So this mechanism does not move energy around. It simply breaks the conservation of momentum. And the other thing is that on the first particle, so there are n particles, and on the first particle, there will be a thermostat, a heat bath, a Langevin heat bath, that tries to keep this side at temperature T minus. The typical thing that have been studied is that you put a temperature on one side, a heat bath on one side at a certain temperature, and another heat bath at another temperature, and you want to see how heat flows from the warmest temperature to the lower. What we do here is something different. On this side, we put a force. We put a force that does a certain work, and it's a periodic force. So it will shaken. There will be a periodic force, will depend on n. It will be time dependent with a certain period. And the period will be, so the force will be of this form. F and T will be, they take a periodic function, will be periodic. It's a certain period, which may or may not depends on n. We see the different cases. And let's see of this form, 1 over square root of n. I will mainly talk about this case, f of t over theta, where f is just the function of period 1, which has some positive frequency. So we say that f of t dt, 0 average, and as a positive. It's not trivial as a positive. So, it's not just equal to 0. So this force is doing work. This work will become heat and eventually flow in the other thermostat. We want to understand in the limit as n goes to infinity how this is happening and what are the equations that regulates this. Now you see that I divided by 1 over square root of n the force if I take a period 1, is because I have to be careful. If I shake too much the chain may break up when it becomes too big. I want to keep break up because there is this stochastic mechanism that stops the momentum to flow into it. So since it will move diffusively inside the heat, the energy has to somehow, I have to be careful not to put too much energy, not to do too much work on the boundary. Otherwise, things will not be stable as n goes to infinity. More generally, you can take period of this type, Fnt. You can put 1 over n to the power a, and then you can make the period being longer, and the scaling with n of the form t to the nb theta. So the case before is a equal 1/2 and b equal 0, but things are stable as long a plus b is equal 1/2. So I cannot, for example, go to a period of the macroscopic time scale, which will be of order n square, which will be the diffusive time scale. Okay, so this is what is the dynamic? Let me write down the equation of the dynamics. Of course, the velocity is equal to the momentum, px, and then we have write down as a stochastic differential equation the equation for the momentum of each particle, the fact that there is an harmonic interaction implies that there is a discrete Laplacian. This is a discrete Laplacian with Neumann boundary condition. Okay, so the Neumann boundary condition means that the convention that q minus 1 is equal to q0. This goes from 0 to n. So there are n plus 1 particles. Then there is the effect of the pinning. So this is the deterministic part. Then on the last particle, okay, there is the stochastic mechanism, the stochastic flipping. So every time there is a change, you have minus twice px of the momentum you had before the jump, and you put here nxt. nxt is a Poisson process, a standard Poisson process. Let's put a parameter gamma here. So nxt is the standard Poisson process of intensity 1, with the gamma will become intensity gamma, and they are independent. And this is the flip of the velocity at each side. Then at the boundary you have in n you have the force dt, and at the boundary in 0 you have the effect, the action of the Langevin thermostat. We put a parameter gamma. So here we can put the same parameter gamma. Doesn't matter. Just to simplify things, P0 minus plus square root of 2 gamma T minus dWt. Wt is just a standard Wiener process. So this is a stochastic mechanism that tries to keep the temperature, the variance of the 0 particle equal to T minus, to this temperature. And work comes from there. Okay, so I already completed here.
Stefano?
Yes.
Is there any reason why the two gammas are the same?
Just to simplify calculation.
Okay.
There's no reason.
Okay.
In fact, this gamma here will not change the macroscopic behavior. What is important, the gamma here, the diffusion coefficient, the thermal conductivity will depend, of course, of gamma. As you know, if I don't put this mechanism that breaks the conservation of momentum, there will be a ballistic movement of energy inside the system and will not be diffusing. All this because we are not able to deal with a nonlinear chain, where maybe in the nonlinear chain there will be no need of such stochastic mechanism to break, to make it diffusive, but that is out of our. Oh, okay, so let me see. So it's okay. These are Poisson process, independent IID Poisson process, and WT. WT is the Wiener process. In this situation, the energy is the only conserved quantity, thanks to the fact that there is pinning. If there is no pinning, there will be another conserved quantity, which is the volume stretch, and Maria will talk more about that situation, but I will mention what happened actually. So if you compute the derivative of the, so let me call the energy of the atom X, it's just its kinetic energy plus the potential energy. So I just attribute the potential energy of the left chain plus the pinning chain. So if you compute the time derivative of the energy as a good conserved quantity, there is a current flowing from the left and another current flowing to the right, since it's locally conserved. So let's call this current J. X is the instantaneous current from x minus 1 to x, minus J, the instantaneous current from x to x plus 1, and you compute it. Jx plus 1 is equal minus px qx plus 1 minus qx. This is for x from 0 to n. Then there is a current from minus 1 to 0. This is the current that comes from the thermostat. This is equal to 2 gamma T minus P0 square. And then there is instantaneous current of energy at the force point. This is the instantaneous work done by the force. This is J n plus 1, which is equal minus Fn. T will depend on time T. That's it. P8, of course, Pn. So the time integral of this will be just the work done. And I will not write down the generator of this process. Let me call GT. It will be time dependent because the force is time dependent. There is something time dependent in it, and will be constituted by, let me call AT the Hamiltonian part, and then S is just the sum of the two stochastic mechanisms inside, the flip of the velocity and the Langevin thermostat. So first thing is, usually when you put to thermostat, you study the stationary state. Here there is not a stationary state because the force is periodic. So what there is a periodic stationary state. And we want to first study, and we need, what are these periodic states? How they are defined? So it will be just a sequence of probability measure in the phase space, dp, dq. When I put a bar below means the configuration of velocities of momentum and position, and T belongs to the period. And then we repeat them periodically. And so these have to be a solution of the forward equation. The joint operator, this is the forward equation that makes evolve the probability measure, but they have also to have the periodicity, which is guaranteed by the fact that the integral from 0 to theta n in dt of the integral of the generator gt applied to some test function big G Q bar P bar in d mu t, this has to be equal to 0. So usual stationary state is this. Now we have to integrate over the period to have the property that is the periodic stationary state. Okay. So the first result is that such stationary state exists and is unique. Not surprising, this is the easy part. Exists a unique periodic stationary state. And now that we know that exists, let's see what the behavior as n goes to infinity of this stationary state, of this periodic stationary state. And so I want to indicate for a function g, when I put the double bracket, I mean the integral over the average over the period of the average over the periodic stationary state. Okay, the double bracket means I'm also averaging over the period. So now let me call Jn this average of the current. This, since there is a conservation law by that property there, this does not depend on x. It's like in the stationary state, but here, since when you average over the period, you have exactly the same thing that happened in the stationary state. So currents, average in time, do not depend on the position where you are looking, because energy is conserved. And the theorem that this behaves like 1 over n, and the limit as n goes to infinity of n Jn exists. Let me call it J. We have an explicit expression for this, just to be computed. And of course, it's negative, and it's strictly negative, because you have energy, you have work done on the right. This energy that comes from the work can only flow to the left. So, but I mean, this is a starting point to understand what's happened after. So there's an explicit expression. If you want, I can write it down. It doesn't say too much. Depends, of course.
Sometimes the work goes to the right, because
yes. Inside the period, it could happen that a little bit of energy gets reabsorbed and you get some energy back. But in the average, you just is negative. And I mean, that is less or equal than 0 is very easy to show by entropy argument, by entropy production argument. That is strictly less than 0, you have to go and compute it.
Stefano, I missed your theorem about existence. Is it difficult to prove, or it's obvious?
No, that's not the difficult part.
No,
but we want to be sure that.
Oh, okay, yeah, because
you cannot really adapt. We actually use it, but there should be a more general theory. We use the dynamics, but they should be okay also for a nonlinear case.
Yeah, because in general, those types of theorems are not so easy.
Well, this is for finite n.
Still,
so you have to construct a Lyapunov function
exactly
that gets control and so on. Now, what is really difficult is to prove that when n goes to infinity, the energy inside does not grow. It grows like n, because as usual in the stationary state, you can take with this unbounded situation, so energy can flow in, and you don't have any information a priori on how much energy can accumulate in the middle. In fact, you will see with Marielle that in the unpinned case, they can have accumulation, but still things will go well. But it's really, I mean, there is the flip mechanism is just not dissipating anything, just keeping the, so you, in principle, you can have, in equilibrium, you will have the same problem, but you have incredible luck that you know the solution. And you know the Gibbs state, and you know that the energy is bound. But when you're in a non-stationary state, you don't know what it is, and then you have really to struggle, and you have to. This is was one of the main difficulties. Okay, so this is a first theorem. So now that we know that the current, typical current goes like 1 over n, and n Jn is finite, let's see what we can say about the temperature profile, the stationary temperature profile, the periodic stationary temperature. to the other theorem. So let's look at the energy average in time, so the stationary state, the periodic stationary state average in time, and then I'll test it against some convergence. Actually, the convergence is stronger than this one. Let me put it this way, because this is probably familiar to most of people. So I take some function phi on the interval 0, 1, and then the theorem says this converge, and then goes to infinity to a temperature profile, Ty dy, and temperature profile is just a linear thing, so Ty starts with the temperature of the thermostat, and then it grows minus, because J, remember, J is negative, so it grows like 4 gamma over a coefficient D times Y. This is Y in 0, 1. This is view macroscopically, you scale everything, you have just an interval 0, 1, and you see this straight line. So what, J, of course, J, Y. So J determines, the current determines dependence of this temperature profile. And the constant D is the one that was already computed in the bulk. The thermal conductivity is D over 4 gamma, where D is equal to 2 divided by 2 plus omega 0 square plus omega 0 square root of omega 0 square plus 4, I think. Sorry, I don't see close and I don't remember by hand. It's something like that. And in particular, when omega 0 goes to 0, in the unpinned case, because T is equal 1. So this is telling you there is a Fourier law. The current is equal to minus D over 4 gamma. Remember, gamma is the intensity of the flip of the velocity times the gradient of the temperature. So in this sense, the Fourier law is satisfied. Well, the thermal conductivity then is given by this coefficient D divided by 4 gamma. This is the Fourier law for this. Now, there are a couple of remarks. I put here the total energy, but I could have put here just Px squared. That is the local kinetic energy, which is the temperature, because here there is no other mechanical energy present, thanks to the pinning. And you will have the same profile. So you will just have the distribution of the temperature, of the empirical temperature, converge to the Tx. This is one remark. The other remark, which is we're doing the calculation, but we are not yet done. The time average may be not important. That means if I just, you can ask yourself, well, okay, if you have averaged on the period, what if you don't average on the period? Just look at the particular time t, and you average out, you send the limit goes to infinity. Then when you are in the bulk, remember, I'm oscillating very, very small as n goes to infinity. When you're far away from the force, this oscillation don't make, when n goes to infinity, the variance, say the variance of the local kinetic energy just goes to 0. So you will have the same limit for every instant of time t, except at the boundary. Okay, this is the result. And then about the non-stationary situation. So maybe, I hate this one. Non-stationary behavior. You have diffusive behavior, so you have to rescale non-stationary behavior. You have to rescale space and time diffusively. So this is in progress. Let's say there's not yet written down the theorem, but we hope to prove this. 1 over n, some I take a function, again a test function, and I take the average. No, I take now the energy at time n squared t. So you see, we scale space and time diffusively. We have seen that many times yesterday. And as n goes to infinity, this will converge to phi of y, a evolving temperature profile, where the temperature profile satisfies the heat equation dT equal d over 4 gamma dYYT. Nothing surprising up to here. The point that the boundary condition in 0, you have, of course, the temperature of the heat bath that I put in 0. But in T, in 1, the other opposite, I don't have a Dirichlet type of boundary condition, but I have a Neumann boundary condition. So the derivative of Ty is equal to J for gamma over D. J, where J is the current of the stationary state. So you see the difficulty that happens. So this is a way to, in a way, to put a Neumann to obtain all Neumann boundary condition instead of Dirichlet boundary condition on the right, and the Neumann band is an inhomogeneous Neumann boundary condition. Instead, we are fixing the derivative there that will be equal to J, and also means that somehow this requires that usually when you prove a dynamic limit, you have to prove some kind of local equilibrium. But here, close to the boundary, it's not local equilibrium, but it's a local stationarity that you have to prove, because basically what's happening that you have to prove that at the boundary, the system is close to the stationary state when you put this force there. The periodic stationary state that you study there. That's the difficulty that you have here with respect to the typical problem you have there. How much time?
3 minutes.
3 minutes.
Before.
No, okay. No, okay. I want to say, then I will not say anything about how these things are proven. I just want to say something about the case omega 0 equals 0 unpinned. And in the unpinned case, there is another conservation law, which is the stretch. The stretch is given by Rx, which is Qx minus Qx minus 1. You can stretch this tension, but you are shaking on one side the system and put in work, and then you have another equation for R, which will be diffusive equation of this type, dt R equal 1 over 2 gamma dy R. And if I'm shaking on a microscopic time scale, like I'm doing there, I will have that there is no tension on the right. So I have R1, RT1 equal to R01, RT0 equal to 0. So this will be a diffusive equation with Dirichlet boundary condition, but the temperature profile will be different because there are two energies here. There's a mechanical, the total energy is the sum of a mechanical energy, which is R squared over 2, and the thermal energy, which is the temperature. The temperature profile then will be 1 over 4 gamma. Remember, D becomes 1 over 4 gamma, dYYT. This will be the normal heat equation. But the presence of the other conserved quantity will change the evolution of the temperature. So there is a positive term, 1 over 2 gamma dy R squared. That means if there is a stretch of the volume, the gradient of the stretch creates an increase of temperature inside the system. Notice there's a plus sign here. Otherwise, second principle thermodynamics will be wrong. So there is there is a diffusion of heat due to the usual diffusive term by the thermal diffusivity, but then there is also a creation of heat due to the fact that there is a mechanical work that becomes thermal energy, and is the flipping mechanism that is doing this. The mechanical work can come also from the force outside. That's what we'll talk about, Marielle. Okay, and that's okay. The boundary condition here, if we do the frequency there, is that the T1 will be equal again to the same boundary condition that Neumann boundary condition for gamma J, where J will be the stationary state. The case Marielle will talk about is when the time will change slower on the macroscopic time scale. Then we will have work done in the sense of thermodynamics, work done in the macroscopic time scale. The work will go inside the system, and then it's only inside the system that will become thermalized and become heat. In this case that we have studied here, the change of work in heat becomes immediately at the boundary because the pinning does not permit long waves to come inside the system. It took more time.
I have a question. What do you mean when you say the nonlinear case would be interesting? You said in the beginning the nonlinear.
When the nonlinear case, I expect similar behavior, but I will not need the stochasticity ideally. But even with stochastic, with the stochastic mechanism, it will be very difficult. But in the nonlinear case, the temperature, the diffusion coefficient will become function of the temperature, and there will be a Green-Kubo formula that tells you how this forms. And the way this appears is because it's become from the mathematical point of view, it's a difficult non-gradient dynamics. But the boundary condition expects similar situation. The scheme will be similar. So
if you speed up the boundary, this periodic boundary by n, by a factor of n, what type of boundary condition would you get?
Speed up.
You have your periodic, right?
Yeah, the period now is a kind of microscopic, for example.
Make it very fast.
It's very fast. And you want it even faster than that.
Yeah.
Oh, if you do faster than that, you want it even faster than microscopic timescale. Yeah. I guess will be some homogenization of it, and we were interested in the case where the period becomes longer. If the period becomes even because, I don't know what it becomes even in the other direction. I didn't really thought about it. I may say something stupid.
Okay, yes, Bernard.
I guess you could get closed form also for the pair correlations of the energies.
For the periodic stationary state. Well, the way we prove it is just we compute all the covariance matrix. The limit of all.
What is the shape of the correlation of energy? Because that was the correlation.
The correlation of the energy. No, that we haven't studied. Not doing compute, because basically, in order to do this, the nice things of the harmonic chain that you can, if you control the covariance of the Q and the P, you have solved the problem. So basically, we just work on that. When you go to force moment, it's more difficult. So because the periodic stationary state is not Gaussian, so cannot really prove that force moment exists. For example, of course they exist, but I cannot prove. The second moment, we are just able to control the second moments, but in principle, as n goes to infinity, the force moment may explode. We are not able to prove that. So certainly we cannot control the covariance. So the covariance of energy will be controlling force moment.
Our question doesn't seem to be the case. Let's say.